Good afternoon, everyone. It is indeed a pleasure and an honor to introduce to you today our own Professor Hitoshi Murayama. Hitoshi received his PhD from the University of Tokyo and then first came to Berkeley in 1993 as a postdoc. He then joined the faculty in 1995. Hitoshi was also the founding director of the Kavli Institute for the Physics and Mathematics of the Universe at the University of Tokyo. He has worked on new physics searches, on particle colliders, on dark matter, on neutrino physics, baryogenesis, inflation, supersymmetry, and fundamental aspects of quantum field theory, amongst other things. Hitoshi was very heavily involved in the Camland neutrino experiment, and I am told that he was even taking shifts on the experiment, and you shared some other scary details of experimental endeavors as well, Utsukare-samas. Okay. And that particular experiment led to the winning of the Breakthrough Prize in Fundamental Physics in 2016. Hitoshi is a fellow of the American Physical Society, a member of the American Academy of Arts and Sciences, and a member of the Science Council of Japan. Most recently, Hitoshi was chosen to chair the Particle Physics Project Prioritization Panel, known as P5. And this particular report then sets priorities over the next decade for this field, and I think it will be the subject of the presentation today. Please join me in welcoming Professor Murayama.
Thank you. Thank you. So let me get started talking about this, the prioritization in particle physics. And you might not be familiar with this, but this kind of prioritization and coming up with a program recommended for the next 10 to 20 years happens in every field of physics. You can see some of the reports actually up here. And nuclear physics just came up with their own report as well. So this is happening in all areas of physics. And if you're actually working in a small condensed matter lab and so on, you might not think of any big prioritization is needed, but some of you might actually use light source. And many of the light sources around the country cost $1 billion and above. So those things also require prioritization to fit into some certain kind of budget profile nationally as well. So this is happening in every area of physics. And things are done slightly differently in different fields. So in our case of particle physics, of course, we start with the community, trying to see what people are interested in doing, what people want to do, and so on and so forth. So we actually organized this community study called SNOWMAS. And it's called SNOWMAS after the city in Colorado called SNOWMAS, Colorado. But that's the place where actually we used to meet for like 3 weeks all together and discuss the future of the field. But SNOWMAS has gotten such a preppy, expensive place to go. So physicists can no longer afford to go there. So recently we started meeting in places like Minneapolis. But anyway, so it's still called SNOWMAS. And this is organized by American Physical Society, Division of Particle Fields. So this is really the bottom-up process. So what do people want to do? And then people come up with all kinds of white papers and so on and so forth. And that's the process that actually took a whole 2 years because of the pandemic from year 2020 to 2022. And then after this process was completed, then the Department of Energy, High Energy Physics, and the NSF Division of Physics came up with a charge what the committee should be looking at. And then they also give us a specific scenarios for future budgets available to this field. So we have to come up with a plan that would fit into the budget profile. And so we had to form this committee, the Particle Physics Project Prioritization Panel, P5 for short, as Irfan already mentioned to you. And so this activity is organized by a standing committee called High Energy Physics Advisory Panel. But there is apparently federal law, which I didn't know about, that says that if we have a standing advisory committee for the federal government, all the meetings have to be taken out in the open. So anybody can come and join, and so that would make it impossible to discuss really sensitive issues like which project is more important over the other. So that's why we can actually do this discussion on this panel. So this P5 is meant to be a sub-panel of HEPAP, which is allowed to meet in a closed session. So that's why we actually formed this panel for the prioritization. And we are supposed to come up with the recommendations, which we did. And they, of course, go back to the people who asked for, namely DOE and NSF. But we definitely hope that we write the report in a way that's accessible to anybody, so that people in the executive branch, like Office of Management and Budget and Office of Science and Technology Policy, would read it and try to implement them in the President's budget request. And of course, finally, budget gets decided by the Congress, so we hope to reach out to the congressional staffers as well. So that's the mechanism. So based on this mechanism, the government knows what the field of particle physics wants to do, and they try to see if that can be actually fit together within the budget they put together by the Congress. So that's the idea. And this is a picture we took at the end of this snowmass process. So this time we're reading in Seattle, Washington. And you see already hundreds of people here. So overall, more than 2,000 people participated in this process. So it is a big deal. And at this meeting, the government official came. Her name is Harriet Kahn, who is now the interim director of entire Office of Science. And she gave a speech on what she thinks are the key elements of successful P5. So she said, we need to be well informed by the science community. That's exactly what we did by having this snowmass process. Set a grand long-range vision for the US particle physics, which means we are putting together a program for the next 10 years, but should be done in the context of a long-term vision. So that's what she's saying. And we need to face budget constraints realistically. So community made tough choices, and because we can't accept everything people have proposed to do. And we need to have a balanced portfolio between domestic and international projects, small, mid-scale, and large projects. And finally, she says community engagement is critical to success because bickering scientists get nothing. And you already see this is a self-contradicting requirement. She's telling us that we need to make tough choices. So I'm supposed to say no to many proposals. But at the same time, we need to make sure everybody is happy. How is that possible, right? It's an impossible task. So when I actually was appointed to actually lead this prioritization panel, I told the agencies that I'm scared to death. And they jumped on it and said, well, that's exactly why you're doing it. What do you mean by that? Well, so apparently they are being bombarded by people who claim, oh, I know the answer already. That's easy. Let me run this process. And that's exactly the kind of people they didn't want. So at least I understood the gravity of the issues. And that's a little qualifications I apparently had to get started with it. So one of the first things I did is to put together a logo for the process. And here's P5, 5Ps. And it's very simple. And actually, I have some philosophy behind it. So the colors of 5Ps were meant to actually based on the Olympic logos. And the overlapping nature of 5Ps indicate that field is also overlapping among different subfields. And it's also very global because the particle physics really work internationally around the globe. So that's the meaning I want to actually put into this logo. But very soon I realized that I'm not going to make everybody happy in this process at all because the 5 rings of Olympic logo refer to continents: Eurasia, Australia, Africa, North America, and South America. And that leaves out Antarctica, where people are putting experiments like CMB and ice cube. So I made them already unhappy. So this is a very impossible task, I have to tell you. But we assembled a panel, and this panel has been really, really amazing. So everybody comes with their own interest in scientific expertise, but they all managed to set their interest aside and try to think of what is the best for the entire field. So I was very, very impressed by everyone on this panel. And there are many people who have Berkeley connection. So Cameron is one of the division directors at LBL. The Jesse Taylor was the middle fellow in Berkeley. Carsten was also a LBL postdoc. And the Beate was on faculty here, who unfortunately left for Daisy in Germany. And the Lindley was a student here working on Cameron experiment, Earthman mentioned already. So there has been a lot of Berkeley connection. And we became very close. For example, the Yuri, who is here, is an experimentalist. But he actually does pottery. So he recently sent me this mug with the P5 logo on it. Very nice. And Kyle Cramner, who is right here, is a specialist in computing. And he just sent me a picture of the total solar eclipse from Arkansas. So we became very close to each other. And in addition to looking at the different projects, we also need to understand how much each of them cost. And that's a very difficult business. And I was just chatting with Chris McKee at the tea time, where he actually led the panel of the prioritization in astronomy and astrophysics 20 years ago, I think. And then he approved the JWST at a cost of $1 billion, which ended up costing $10 billion, as you might know. So understanding cost is difficult. So I called on another Berkeley-related person, Jay Marks, who used to be in Berkeley but became the director of the LIGO laboratory. So he knows how big projects go. And together with him, we assembled a group of people who have experience in running big projects. So they have sort of the gut feeling when you look at the cost estimate, well, this can't possibly be true. So they actually helped giving us an advice on what the cost actually may be. And that really helped us understand the maturity of cost estimate that we can actually move forward in actually putting the program together. So the standard joke in the community is that when physicists make an estimate of the cost of a project, they tend to go off by a factor of pi.
That's great.
And then we have to actually go through the process of getting information from the community, and that is the information gathering phase. Of course, Snowmass was the beginning, and we conducted 4 town halls. First one was actually held right here in Berkeley, and so that we actually listened to the community, get all the information about what people want to do. And then comes the deliberation phase where we have the closed meetings. We had 4 in-person meetings, and that's where we really had to discuss difficult questions about how to prioritize and choose the projects we eventually would recommend. And just to give you an idea how hard job that is, so they give us these budget scenarios. And this favorable scenario, what we call, is called A. A stands for all for. It assumes 2% increase every year, which doesn't catch up with inflation. So that's an erosion by something like 1% every year. The baseline B scenario is the better scenario because of the initial hike. Thanks to this law called the CHIPS and Science Act, it assumed 3% increase after that. That sort of catch up with the inflation. So inflation is somewhere in the middle between these 2 curves. And just to get an idea on how tough job you are going to face, so typically we spend about 30% of the budget into new projects. So they correspond to these 2 lines. And let me blow them up. And just putting in all the projects the field is committed to already, that already overshoots the budget given to us. And even setting aside some of the bigger ticket items people thought about, like multi-billion-dollar projects, the rest is more than twice the budget we are given to us. So we have to do a real prioritization here. We can't say yes to everything, and that's where things become very tough. And so when I realized that this is going to be a really tough job making everybody unhappy, so I actually asked Linda in our group, she's a postdoc, to make a meme that I'm the most hated man in the community. Anyway, so at the end of the day, we came up with a report, which the title is Exploring the Quantum Universe, Pathways to Innovation Discovery in Particle Physics, that was released back in December. So when you hear this word particle physics, I'm sure everybody thinks of this kind of science, looking at the fundamental constituents of matter. So here are my kids, and my daughter is actually sitting over there today, and they are made of molecules. Molecules are made of atoms, and atoms are made of electrons and nuclei. Nuclei are made of protons and neutrons, and protons and neutrons are further made of quarks bound together by the gluon. So trying to look for what are the fundamental constituents and how they actually glue together to build material around us is definitely a hallmark of particle physics. But in the US, the particle physics got really expanded to embrace cosmology, thanks to actually 2 people here in Berkeley. And George Smoot wanted to understand the universe in the past, and he managed to take a picture of the baby universe and show that there was small variation in densities at the level of 10 to the minus 5. And this is actually a very important density variation because this variation eventually grew to form stars and galaxies, and hence us in the universe today. So this was the seed for everything that followed. And of course, discovery of this density fluctuation is what earned him a Nobel Prize. On the other hand, Saul Perlmutter wanted to understand the future of the universe, and he wanted to see how universe would end up with. And what we learn in school is that when universe starts with a Big Bang, everything spreads out, but everything spreading out would be pulling each other by the force of gravity, so the spreading should slow down, right? That's what we thought for 70 years. So he wanted to know whether it's slowing down to the extent that expansion would stop, then start to actually fall down and collapse in the end, or does it keep going? That's the question he wanted to understand. That's why he wanted to start measuring how the expansion of the universe changed over time very accurately. And to a great surprise for everybody, he discovered the universe is speeding up instead. And that is apparently caused by this mysterious subject called dark energy. We have no idea what that is yet. But anyway, so that's what he did. So talking about the birth of the universe and how the universe has been expanding ever since and into the future became part of particle physics. And since then, of course, the data got more refined, and we also confirmed the acceleration of the universe very accurately these days. But anyway, so this became also part of particle physics. So one of the first things the panel had to do is sort of define who we are, what is our science, what we would like to understand. So we came up with 3 science themes that we believe would define the field of particle physics. The first one is, again, looking at the smaller and smaller objects. And that's a science theme we call decipher the quantum realm. The other one is looking at a subject that is getting bigger and bigger, namely the universe. And this is the area we call illuminate the hidden universe, because we don't see dark energy in telescope. Dark matter is another thing we don't see in telescope, but surely it's very important to us. How we got started is called inflation. We haven't actually seen that either. So there's a lot of hidden things in the universe we like to understand. And we have a theory called the standard model of particle physics describing this side, and also the lambda CDM model of cosmology describing that side. But we know both of them are incomplete theories. We are still missing something in a big way. So to get a full understanding of what's going on, we really need to see what else is missing. And hence, this science theme is called Explore New Paradigms in Physics. So what we did is take one word from each science themes and came up with this title, Explore the Quantum Universe. So that's the meaning of this title. And under each of these science themes, there are pressing questions we like to understand, which we call science drivers, that have to do with the neutrinos, Higgs boson, dark matter, and what drives the cosmic evolution. And looking for new things, we need to discover new particles, or also look for quantum imprints of new phenomena. So these are 6 science drivers. And if you look very closely, actually spend hours and hours working with a graphic designer that came up with what we call the mural, you see these things are neutrinos, which is both particles and waves, and that's why they can oscillate. You see a Higgs boson thrown to the bottom of the potential here and stuck there to break the symmetry. And you see the dark matter emanating from the collision in the middle, maybe LHC or Big Bang, and this may be black holes and stuff, so they're actually not in there. But showing this graphic is too complicated each time, so we drastically simplified it for the branding purposes and came up with this simple logo. So the left-hand side shows looking into smaller and smaller object. Right-hand side shows looking at objects that's become bigger and bigger, named the universe. And they intersect in the middle, and they cannot be separated. So that's a single science for particle physics. So that's the meaning we want to indicate with this logo. So now I jump into what we recommended. And I don't read through all the textual recommendation, but the important thing is that, first of all, we looked at the ongoing projects and see if they're really worthwhile continuing on. And after a lot of discussions, we eventually decided, yes, they are worthwhile continuing on, like going for the 10 times higher data rate at the Large Hadron Collider, looking at the neutrino experiment that is now being built. And new telescope that is being developed in Chile is also a part of the particle physics, according to this definition. So we like to keep going on these projects. And not only these big things, there are also medium-scale projects that are ongoing. And whenever there's a big Berkeley involvement, I put this CAL logo next to it. And some of them has to do with looking for black holes using Antarctic ice, because neutrinos can come and interact with it. Or DESI, that's a telescope project where you map the positions and speeds of millions of galaxies. And then the LZ, that's an experiment looking for the dark matter in underground experiment using liquid xenon and so on and so forth. So ongoing experiments are really very interesting. So I already mentioned DESI, that's a dark energy spectroscopy instrument. And this experiment is really led by Berkeley and has already produced an interesting result that the dark energy I mentioned may be actually changing with time. And that already made the New York Times article a tantalizing hint that astronomers got dark energy all wrong. We'll see. So this is already the beginning of the data, so we will see how that will develop, but it's getting very, very exciting. In addition, we came up with the 5 new initiatives we would like to start getting on this decade, and I don't go through this list again, but jump into the science of each one of them, and slightly in a different order, and let me jump right into the neutrinos first. So why do we care about neutrinos? So they are very interesting particles. They are electrically neutral, interact so little. As we speak, there are about 1 trillion neutrinos going through your body every second. Does any of you feel that? You are being hit by neutrinos? No? There. Thank you. You should go to hospital today. So the reason we care is that many of us think that they played a very important role in the history of the universe. So when looking at the Big Bang and beginning of the universe, there was a huge amount of energy. And that energy turned into matter. But the laws of physics we know tell us that when energy turns into matter, that is always accompanied with antimatter, 1-to-1. So if it stayed this way, then eventually matter and antimatter would meet, and they would annihilate back to pure energy, and the universe would be empty, so you wouldn't be here listening to me today. So something must have happened. And so what happened is that somebody, at some point, somehow, managed to take 1 antimatter out of 1 billion and turn that into matter, so that there is a difference of 2 out of 1 billion or so. And the only matter particle we know of who may have possibly done this is actually neutrinos. Because when you think of antimatter, and this is the birthplace of antiproton, proton has a positive electric charge, antiproton has a negative electric charge, and because the electric charge is conserved, the antiproton can never turn into proton. And same with the positron and electron. But for neutrinos, the neutrino is a matter particle with 0 electric charge. Antineutrino has -0 electric charge, so they are the same. So they may have turned between matter and antimatter and could have done this. And if that's the case, pretty much all of them would annihilate away, but the 2 of them remain, and that's you. So that's a very important role. So if this is true, the neutrinos might have been the superheroes who saved us from a complete annihilation. So they get a lot of credit for that. But have they really done it? So we need to understand the properties of neutrinos exquisitely well. That's why people built this a major facility in South Dakota in an underground experiment. So the idea is to create the neutrinos artificially using particle accelerator at Fermilab in Illinois, and send the beam of neutrinos all the way to South Dakota and see if they turn into something else. And that is what is called the neutrino oscillation experiments. And first phase is already being constructed. The cavity is already dug. So construction's in full steam right now. So you might say, isn't that already enough? It turns out that previous P5 report said you start with an exposure of per unit 120 megawatt kiloton a year. So megawatt is the power of the beam. Kiloton is size of the detector, and year is, of course, time. So this is how much data you accumulate. So this is basically referring to data size. So this is a good start, but you have to get to 600 megawatt kiloton a year eventually. And that would require making the beam twice as more powerful, and also doubling the number of detectors. And people looked into this idea and estimated how much it's going to cost. It turned out that we couldn't do this within the budget given to us, because if you want to double the beam power, you need to build a brand new accelerator, and that would cost billions of dollars, unfortunately. And part of the problem is that this is really silly. The existing accelerator called Booster has an office building sitting on top of the ring. So if you increase the beam power, that will cause radiation to people who actually live in those offices. So it's really silly, but that's the limit, and so we can actually do that. But we figured out we can double the beam, but we can get close to it by making some small modifications to the accelerator that already exists. And then this can get started earlier so that we don't need to build one of the detectors either, and that's the way we can actually fit this into the budget. So you can see we have to go through this kind of creative thinking by preserving the science, but somehow reduce the cost, that we can actually put it together into the given budget profile. So this was the first step of that. So, and given that we actually not recommending to build the fault detector right away, but there's already cavity dug, we recommend the community to look into the possibility of coming up with a different design of the detector to enhance the science, not only looking at the neutrons coming from the beam, but possibly those coming from the sun, coming from supernova explosion in the galaxy, or maybe some other sources. And so we'd like to expand science that way. So we preserve the science originally recommended by going to a cheaper option, and we may even do more science this way. So that is the way we actually make a recommendation. Now coming to the Higgs boson. We know the sun burns because of the nuclear fusion process inside. But if you have looked at the eclipse today, which you shouldn't have, then the only thing you could have seen is the surface of the sun. You don't know what's going on inside because it's a thick ball of hot gas. You don't see what's going on inside. But this nuclear fusion process is supposed to be happening at the core of the sun. And how do we know? Well, we actually can see it because of these neutrinos. Because neutrinos interact so little, they just stream out all the way through the sun without any problems, and they are shining on you right now, right here. And by using a big detector like Super Kamiokande, you can actually catch those neutrinos so that you can actually see the center of the sun if you use neutrinos. And here's the picture. You can really see what's going on inside the sun, and this is the picture of it. So that's how we know that this process is indeed happening inside the sun, which involves a new force called the weak force, or weak interaction, which is also responsible for nuclear beta decay. And the nature of this force has been studied in great detail by using particle accelerator at CERN in Europe. And eventually we came to the conclusion that weak force is almost exactly the same kind of force as electricity and magnetism you are very familiar with. But there's one big difference. Electromagnetism is a long-range force. If you hold a compass in your hand, the needle will point to the magnetic North Pole. So North Pole is pulling what is in your hand, so it goes over long distance. But the weak force goes over only 10 to the minus 16 centimeters. It's a very, very short-range force. We believe they are of the same kind, but somehow they behave very differently. And that was a big puzzle, what's going on there. And in particular, this distance of 10 to the minus 16 centimeter is just right. If this is much longer range, then the whole world will become radioactive, and we wouldn't be able to live in such a universe. If the range was much shorter than that, then the sun wouldn't burn, and we wouldn't be able to live in that kind of universe either. Somehow, this is just right, which we haven't understood why. And there's this question, why has the two same kind of forces became so different? One remained long range, the other became short range, is something we learned from our condensed matter friends, namely a superconductor. So we all know that magnetic field doesn't penetrate much into the superconductor. So magnetic force is actually a short-range force in a piece of superconductor. And that is thanks to the condensate, or what is called the Cooper pairs, sort of the bound state of two electrons that is condensed in this system. So just imagine that you are living inside a piece of superconductor and trying to understand why the magnetic force is short-ranged. And after a lot of thinking and doing experiments, you figured that there is a condensate of charge 2 that disturbs the magnetic field. But you don't know what exactly that condensate is. Is it a pair of electrons, which turns out to be the right answer, or something different, or something, an elementary particle, or what is it? And that's very difficult to figure out if you're living and dipped right inside it. And you also don't know what is responsible for these particles to condense, because you can't swap the entire universe with another universe made of different isotopes. That's what people did to figure out the phonon is responsible for this condensate. So that's very difficult. So the only thing we can do, dipping inside this system, is to do the measurement as precisely as possible. So we need to understand this condensate particle very well. And that particle is called the Higgs boson. that was discovered in 2012. That became big news around the world, and it was very, very exciting, and the people in Berkeley played a major role in that. But we still don't understand this particle very well. The one thing we did learn is that our universe is filled with the Higgs boson. The Higgs boson were flying apart very, very fast at the beginning of the universe, but eventually they start to slow down as the universe expanded and cooled. And at some point, they froze in empty space, and we're living in that ice. And that ice doesn't have electric charge, so photon doesn't notice it and keeps going with the speed of light. But all the other particles we know of actually get disturbed by the Higgs boson that's frozen everywhere in space and get slowed down. And that's why how they acquire mass and can go slowly compared to the speed of light. And we need just right amount of Higgs boson frozen in empty space so that we could live, as I mentioned just a second ago. So if for some reason the Higgs boson frozen in the universe today would evaporate, then the electrons inside an atom would start going with the speed of light, and atom would disappear instantly. And never mind that I'm so old to have a picture with Einstein and even speak of the full color picture, which is really amazing. But anyway, the point here is that both of our bodies would also evaporate in a nanosecond if Higgs boson were not there. So the Higgs boson is actually keeping us in one piece. That's also another very important role, especially that it's filling up the entire space to keep us in one piece. But we don't know why this particle has got frozen in empty space. And in particular, there's some object called the frozen in empty space is something called the boson condensate, which people can study in the laboratory, like Dan Stamperker, I don't know if Dan is here, in the department. But if the force among this condensate is attractive, then the condensate is unstable and would collapse to a point and then bounces back and explode. And this is a phenomenon really seen in the laboratory. It's called the bosonova, kind of similar to supernova. But we are not seeing that kind of explosion happening in space. So something has to keep it stable, and exactly how, we don't know yet. And the Large Hadron Collider is mass-producing Higgs boson and studying it in great detail. But it's kind of hard because every time you collide the beam of protons at the Large Hadron Collider after an upgrade, you see this huge, complicated mess happening at any moment. This happens every 25 nanoseconds, by the way. It's a very difficult environment. So the reason why you get this kind of complicated situation is that what you're throwing at each other is proton, which is like a cherry pie. And when you throw cherry pie against cherry pie, then of course the goo would fly apart. And that's the goo you're seeing in this picture here. It is a lot simpler if you can actually strike cherry pits against cherry pits, so you don't have the goo. But you immediately see that that's technologically more difficult things to do, to throw something small and make sure they would meet. But that's the idea for the electron positron machine. And technology has advanced to the point that we believe we can actually do this kind of experiment, that we can get much more information that LHC cannot provide at this moment. So people actually proposed to build such a facility, namely E plus E minus Higgs factory in the US. But once again, it was clear we can't afford this. It's going to be, according to the estimate of the European project, it is going to cost 15 billion euros. And we can't afford that, unfortunately. So what we recommended is rely on the generosity of people in Europe or in Japan who are thinking about building such a facility that we can join forces. So we recommended to join an offshore Higgs factory to actually get started with this very important science. And so that is going to be an electron-positron collider covering center mass energy from 90 to 350 GeV. Once you get up to 250 GeV, you can start producing Higgs boson and study them in great detail. And not only that, we would like to understand Higgs boson per se, we also are looking for the possibility is that Higgs boson actually may talk to dark matter and decay into dark matter and disappear from your experiment. And that is the idea called invisible decays. There may be other exotic possibilities too. So Higgs boson can become a tool to look for new phenomena, new particles that way, and that's why we're excited about joining forces and build such a machine. But eventually, we really need to understand how this frozen Higgs boson is in a stable configuration today. Namely, we need to understand how Higgs boson would interact among each other. And to do a job which is better than what the LHC can do, like factor of 10 improvement in a measurement, that would require new technology we don't have today. So one idea in Europe is to have a ring which is more than 3 times bigger than the current LHC, so circumference is 91 kilometer, and run protons inside like what we are doing today, but that would require a very high field magnet, and we don't have technology for it yet. We still have to develop it. Another idea that became very popular in the US is to collide muons instead of protons. And you might remember muon in freshman physics homework, that muons are produced at 20-kilometer altitude from cosmic rays. They somehow manage to reach the Earth, even though their lifetime is only 2.2 microseconds. Now, normally, you would think they can go only over less than a kilometer with that kind of lifetime, but they do reach the surface because of time dilation. Once it goes fast, time gets stretched, they live longer. So the muons live only for 2.02 microseconds, but if you actually, first of all, make them, and collect them, and cool them, and accelerate them, and collide them against each other in a big hurry, you might be able to make it. And once you accelerate them, then time gets dilated, so they can actually make this ring thousands of times, even with this short lifetime, then you are in business. But all of these processes of making them, collecting them, cooling them, accelerating them require also a new kind of technology, so we need to do R&D. So we don't know if either of them would going to work out, but science requires it, so we recommended to do the R&D towards this technology. And especially if this muon collider would work out, we can go to 10 times higher energy than LHC with a footprint which is actually a third of the LHC, and can fit within the site of Fermilab laboratory. And being small, hopefully, would also mean rather inexpensive, but we need to see. So we recommended R&D. So R&D will allow Fermilab to continually expand the accelerator complex while producing the world-class science. And that effort we call the muon shot. Of course, it's meant to be like a moonshot. So that's a recommendation we made, and it's at the top here, to support vigorous R&D toward cost-effective 10 TeV collider in the future. In addition, we identified 4 areas that need reinvigorating: theory, computing, accelerator, and instrumentation. So we made a recommendation to put more money into that too. And once you actually can build such a machine, and we can really look for new particles and look for the quantum imprints of new phenomena. Now, dark matter. And we know dark matter exists. So this room is actually somewhere around here in a galaxy. And it's actually away by 28,000 light years from the galactic center. So our solar system is actually revolving like this inside the galaxy. So something must be pulling us to keep us inside the galaxy. But we know there doesn't seem to be enough gravity from stars alone. So as you know already from the freshman physics class on Newtonian mechanics, maybe even high school, is that if you move away from the sun, the farther you go, the gravity becomes weaker, so the planets have to go more slowly, and that's exactly the case like in this plot. But in the case of our galaxy, even though you go farther and farther away from the center, that it doesn't seem to slow down. But something is wrong. And what is wrong is our assumption that we thought the galaxy is made of stars only. That assumption is wrong. Otherwise, you can't explain this behavior. So our galaxy is supposed to be filled with stuff we don't get to see, but they exert gravity on us. And that is the object we call dark matter. And when Joe Biden introduced the first picture of JWST, I hope he learned that picture he was showing to the nation has showed an evidence of dark matter in it, my name is looking at this gravitational lensing of the giant arcs where the galaxy looks so warped just because of the gravitational pull of the dark matter inside this cluster of galaxies. So dark matter does exist. We are sure of it. But we don't know what it is. At the same time, we know it also played a very important role, namely in the kind of universe that doesn't have dark matter in it, that's a wrong universe. We know the universe started out with this tiny density variations, which George Smoot told us at the level in 10 to the minus 5. And it just stays that way. And there's no density contrast growing, and there wouldn't be any stars and galaxies, and hence us. But in the true universe with dark matter, the tiny dense region has a gravity to pull more dark matter in, becomes denser, the gravity becomes stronger, pulls even more dark matter into it, and gravity becomes even stronger. And then density contrast grew, and then was birth of stars and galaxies and us at the end of the day. So dark matter actually made us. I personally regard dark matter as my mom. She has grown the primordial elements into us and assembled us. But because this is still something we don't know yet, we haven't met our mom yet, so people are trying to do that by building all kinds of experiments today. But we have been actually focused on one particular mass region for dark matter, which is called the WIMPs. But after a lot of studies, we actually realized that the possible range of the dark matter in its mass ranges over 90 orders of magnitude, and we don't know where it is. We've been looking very deep in this particular mass range, and some people thought the axion may be another candidate, but there are a whole lot of possibilities people haven't studied yet. So if you think of particle like dark matter, it could be lighter or heavier than the WIMPs we have been looking for. If you go to a very light object, they become, again, a Bose-Einstein condensate and start to behave like a classical wave instead. If you look at a very heavy object, they may be composite or macroscopic or even black hole. And we have no idea where dark matter sits in this plot. So there's a huge discovery space. So we have gotten started with the WIMP, so we should better finish that job. But there's a whole swath of possibilities we haven't looked yet. So even the small experiment, small effort might actually take a first look. And there may be low-hanging fruit to discover something major. So that also needs to be pursued as well. So the one direction is that we really would like to finish up this job with WIMPs. And the current experiment is already constraining how strongly dark matter will interact with the ordinary matter. And this number is already very tiny, 10 to the minus 46 square centimeters. So dark matter is interacting with ordinary matter at least 10 times weaker than neutrinos. That's very, very weak. But next generation experiments will come to the level of sensitivity that even the neutrinos will start becoming a background to the search. And that's an incredible sensitivity. People think they know how to get there. So our recommendation is, okay, that's a very clear goal. Why don't we go and get there to see if we can find WIMPs in this mass range? And that has to be done at SURF. That is not meant to be this SURF, but rather a Sanford underground research facility in South Dakota. That's the same place where people are putting together this humongous neutrino experiments already. So that's the recommendation. But in addition, there's the huge discovery space we haven't looked yet. So we recommended a new funding line called ASTE, Advancing Science and Technology Through Agile Experiments, to support that kind of small initiatives to get started looking for various possibilities for dark matter. And it's not limited to dark matter. You can also propose different experiments too. And we believe that's very important, especially for early career scientists, because if you like to graduate and get PhD in 5 years, you would like to be involved in an experiment that can be done in 5 years, and hence agile experiments. And I was very impressed when the subcommittee of this panel came up with this name ASTE, because apparently in Latin, the ASTE means javelin. So it has a clear target, and you can go quickly there, and that's the meaning of ASTE. So I told them, I'm so impressed, you guys know Latin. But they confessed, well, we actually looked up ChatGPT. Anyway, so this kind of small experiments can go a long way, especially in the case of dark matter. And the Berkeley people are already heavily involved in this. So let's get them started to actually build such an experiment is one of our recommendations. In addition, I already mentioned that people are using the ice sheet in Antarctica to actually build a humongous experiment looking for neutrinos coming from the black hole outside the galaxies or inside the galaxy. And so this is already as big as 1 cubic kilometer. It's a huge experiment using this ice. And there's a proposal to actually expand this 10 times bigger. And they actually come to the point that they have just observed one black hole outside the galaxy using the eyes of neutrinos. And as I mentioned to you already, neutrinos can get through pretty much everything. So out of this dense area in the galactic center surrounded by dust and stars and gas and everything, neutrinos can just zoom right at you so that we can see back into the black hole. And that's the kind of experiment they have been doing already and demonstrated. So if you make it 10 times bigger, I'm sure we're going to see more of those. So that's the proposal. Finally, cosmic evolution. So after the study initiated by Joe Smoot and also Paul Perlmutter, we came to a very strange picture on how the universe came to be. The universe we see today, the whole 13.8 billion light years of stretch, was smaller than the size of an atomic nucleus. It was actually as small as 10 to the minus 30 centimeters. It was a microscopic universe. That's how it began. But it got stretched enormously by a process called inflation, an incredible expansion that would actually turn the size of coronavirus into a size of galaxy in an instant. And that's actually part of the standard thinking in understanding the origin of the universe today. And when the whole universe was that tiny, and of course, quantum mechanics ruled in such a small universe, and so that the universe was filled with the quantum fluctuations due to uncertainty principles. And these quantum fluctuations got burned into the universe, which you could see in terms of this tiny variation of densities, as George observed already. And then I already told you that this tiny variation in density have been grown by dark matter so that they eventually become stars and galaxies, and hence us. So in some sense, everything came from quantum fluctuation. You came from quantum fluctuations. That's the theory. Do we believe that? Can we test that? And that is actually a very important question in physics today now. So in some sense, the inflation provided seeds of the density fluctuation that was grown by dark matter. So I personally regard inflation as my dad, who have sowed the seeds grown by dark matter as mom, so that we were born. So I'd like to meet my dad too. And if this is the right idea, the quantum fluctuation probably should have a very simple Gaussian distribution. And looking at the picture of the temperatures, indeed, they follow a beautiful Gaussian. And inflation must have lasted at least for a certain period of time so that you produce the quantum fluctuation at the same amount over a period of time. And indeed, the data shows that amount of fluctuations is about the same over 3 decades in the time scale. So all of them provide very good circumstantial evidence that inflation was right, but we don't have a direct evidence yet. And George actually put together a video which explains all this theory about how we came to be. So let me play it.
I really admired the band, and so when they said we wanted to react to the Big Bang with the guys from your lab, I said, no way, I want the band. Okay, so now I got to tell you what the Big Bang is so you guys can do this before the sun goes down. Okay, so the idea is everything in the early universe was packed together very densely. It may have gone for infinite. We don't have infinite people, so we just have to use what we got. And everything stretched, right? Everything got bigger. And the further away you are, the faster you go. So we're going to want to start at the beginning with everybody packed dense and jostling around and playing high tempo rapid. 1, 2, 3. Then the bark Everybody
People
moves
running,
apart.
there we go.
The people on the outside moving faster than the people on the inside. And there's a little bit of irregular motion, so
quantum
miss some
fluctuation.
steps. Okay? I know you can do this. Right? And then what happens is you're going to coalesce together in groups of 6. Right? So you have to find 6 buddies. And half of you are going to form spiral galaxies. 3 people facing one way, 3 the other, and you rotate slowly as you move out. And the other half form elliptical galaxies, which are round blobs that keep moving out. So now, there's a brass section out there called tubas. They make a really spectacular spiral galaxies, a really big one, like our own galaxy or like Andromeda. So you guys get to be near the middle, and you get to make a really cool, you don't have to run out so fast, but you get to be able to orient where half is facing the other way, and you get to rotate with a sort of twist up. And you're like the centerpiece of this whole thing. Go tubas. Great, guys.
It makes sense, right? And I have to remind you that 80% of the band members are invisible dark matter. You don't see them. George himself is sitting at the center of a Milky Way galaxy, apparently, so he's a supermassive black hole. You don't get to see him either. But anyway, this is how the universe evolved. That's what we think, and we'd like to get a direct evidence of that. So the program we recommended basically does the following. So all you can do with telescope is stare at this picture of the baby universe when the universe was already 380,000 years old. And it's just like the surface of the sun. You can actually see through it once the universe becomes so small and dense and hot. This is the wall. You can never see anything beyond this directly with any telescope you might build. It's not a technology limit, it's a fundamental limit. But what we would like to understand is what was going on before then. And we managed how to understand when the universe was actually 3 minutes old. That's the time when the protons and neutrons zooming around the universe would start to stick with each other. And that's something you can simulate in the laboratory using particle accelerators. And once you can actually make this happen in your lab, you can estimate how much of them actually did happen in the early universe, and then come up with prediction that the ratio between hydrogen and helium should be 3:1. And in fact, if you use telescope to observe the sky and try to measure how much there is in the universe for hydrogen and helium, and they are indeed 3:1. So that way, knowing the helium coming from the Big Bang is what is actually telling you how the universe looked like when it was 3 minutes old. And we can go further. If dark matter is indeed WIMPs, I mentioned to you earlier, then they were born when the universe was less than a millionth of a second old. So that's how far back we can go to understand how the universe looked like to let the dark matter be born in the beginning of the universe. And if you look at the Higgs, how it got frozen into empty space is presumably a kind of phase transition that happened when the universe was about a billionth of a second old. And that's an important moment where the universe changed its phase from gas of the Higgs boson to an ice of Higgs boson. That's something we'd like to understand. If the neutrinos managed to reshuffle matter and antimatter, that presumably happened much earlier on. We don't know exactly when, but goes back towards the beginning of the universe even closer. And inflation is really the beginning of everything. And why the universe getting inflated? Like you're stretching a rubber sheet, then whole space and time starts to wobble. A wobbling space and time is nothing but a gravitational wave. But gravitational wave can punch through this dense plasma in early universe without any problems, like neutrinos streaming out of the sun. So those gravitational waves are still supposed to be there, jiggling space and time the whole time. And they also jiggle the photons coming from this, the baby universe. And it produces a particular kind of polarization called B-mode polarization. And if you can actually see this B-mode polarization, that's the way of looking back at inflation and get direct evidence for it. So this is the program we recommended in the P5 report. And in addition, as Saul Perlmutter already started, we'd like to understand the future of the universe as well, namely trying to understand the nature of dark energy that's driving the expansion of the universe today. And those projects we recommended as well. And to do this experiment, you actually need to go to South Pole as well, just like this ice cube experiment in Antarctica, because the great thing about South Pole is it is at the pole. If you build a telescope dish looking upwards, no matter how Earth rotates, you're still staring at the same patch of sky. On the other hand, we also need another site in Chile, but this dish will point to different directions every time Earth rotates around. So the site at Chile will scan the universe, but site at the South Pole really focuses on one particular patch of the sky, and that combination is supposed to tell us if the inflation really happened. One thing we learned, though, is the South Pole site is actually a little bit of a limbo. So there was this letter issued by National Science Foundation. It says South Pole Station is saturated with already funded projects and required critical infrastructure and maintenance activities that cannot be deferred until late in the decade. So we can't do new experiments at South Pole, they say. We have to actually somehow reverse that because we would like to get us started with it. It's a little complicated because our report goes to this part of the Mathematical and Physical Sciences Division of NSF, but the South Pole is maintained by Geosciences Division, which has this Office of Polar Program. And in principle, they don't need to listen to us. So we actually invited them to a meeting 3 times to make sure that we are on their radar screen and they will listen to a plea. For example, one of the problems that they use this military cargo plane run by Air Force. And you can see that actually it has sleighs at the bottom instead of wheels so that they can land on the ice. But they were built in the 70s, and they're getting old and going to retire soon. But right now, there's no replacement plan by the Congress. So that's another area we have to work hard and advocate that we need to maintain a strategic U.S. interest of having presence in the South Pole for science. So that's why we said the South Pole, a unique site that enables the world-leading science of CMBS4 and IceCube Gen 2, must be maintained as a premier site of science to allow continuous leadership in these areas. So that's another recommendation we made. Finally, the diversity, inclusion, equity are very important. And we said things like the inherent curiosity driving our exploration of the natural world is a universal aspect of human nature. This shared curiosity serves as the driving force behind our commitment to strengthening and expanding this workforce, prompting us to actively seek talent from all corners of society, regions of the country, and on a global scale. So we made specific recommendations on how to promote diversity in our field too. So that was our report. And after we put out the report, there was indeed many people, the reporters from the media, actually watching the presentation at the HEPAP. And out came out actually a fairly large number of news articles. And this article was in Science, written by Adrian Cho. I was very surprised to see the title, Particle Physicists Dream Small. What? We thought we were very ambitious. And it turned out that it's actually not meant to be a bad thing, because if you read the text, particle physicists in the United States have released a long-range plan that looks less like a child's wish list and more like a parent's cautious budget. So, no, we are being responsible fiscally. A New York Times article really picked up on this muon chart. That's a great idea. They even complained for us that the meager federal budget could limit its ambitions. That sounds great. And the Science, actually, the latest volume of Science featured this muon chart even on the cover. So it's actually a good read. I recommend you to read it. And one reporter who has been actually rather critical of a field is Dan Garisto. And at the end of the snowmass process in Seattle, you see the Space Needle, he wrote an article, physicists struggle to unite around future plans. People are talking about all over the place on all kinds of different things. How are they going to agree on anything? And that's what this article said. But after P5 report, he wrote another article which said roadmap of US particle physics wins broad approval. And even better, he tweeted. And this is what he said in his tweet. When snowmass ended last year, I wondered how particle physicists were ever going to reach consensus that worked within the budget, was still ambitious, and didn't alienate huge swath of the community. Somehow, the P5 report does all of this. Yes. That's exactly what we're aiming for. And after the report was released, we actually collected signature of support from the community, and then in the end, we have more than 3,000 signatures out of the community of probably like 5,000 physicists, so it's a very big fraction. Still, we did say no to quite a few proposals. In this table, it shows solid black, meaning no, and we had to say no to these projects. So certainly, I was still worried that I would be in this situation, but given that there is fairly broad support by the community, it may be not as bad as this, but it may be actually more like this one instead, was drawn by my another daughter. And so, I think I'm feeling better now. And now that this report is done, I've been briefing the staff at the Congressional Staff Person Appropriation Committees, and that briefing went quite well, according to Harriet Kahn. I also briefed the Office of Science and Technology Policy, and she told us that you guys keep getting better and better in presentation. That's great. And at this meeting, I emphasized the problem with the South Pole. So they already invited the proponents of the CMB experiment, ice cube experiment, and also a glaciologist. There are many people who rely on the South Pole location, climate science, microbiology. So these people also need access to South Pole. So now they're at least showing interest in actively working on that. So that's great. We'll see how that would actually move forward. And I myself, together with the other panel members, now have to sort of publicize what we came up as a recommendation, what kind of program we put together to a wider community like this one here at the various physics departments, also going to different countries and talk to their funding agencies and their communities. So there have been many number of talks given by all the panel members. And here we are today at UC Berkeley. So that is my Eras tour on particle physics. And here's me. So that is what I'm doing today. So I'm going to fly red-eye tonight, going to Washington, D.C., and visit the Congress and talk to them about what particle physicists want for the next 10 years. So that's the program, and we are very excited about that. Thank you.
Thank you, Hitoshi, for a wonderful talk, and of course, congratulations on a tremendous milestone. Questions for our speaker? Yeah.
This one?
I don't understand why without dark matter, the state of the universe would be better.
Can you say it again?
I think you said the fate of the universe would be better without dark energy.
Yeah, so the dark energy, as I told you, is speeding up the expansion. So if dark energy is really, really strong, it may actually make the expansion infinitely fast at some point. Then the whole universe gets ripped apart, and that will be the end of the universe. So if dark energy is dominant, we may be heading to a grim fate. So I think that's what he's referring to in his overview, that without dark energy, if it's actually weakening, that's what data seems to be suggesting, then we may not be facing that kind of grim fate. And that is what I is saying, good news for the fate of the universe.
Even without dark energy, the fate of the universe has already been determined. So it's a matter of time, but the fate of the universe cannot be changed.
So the fate of the universe is that if dark energy is weakening, as this new data set suggests, then even though we are expanding with ever faster speed, it's accelerating, we would eventually turn into decelerating universe once again. And then, so of course, universe keeps expanding even in that case, and you start losing the size of faraway galaxies, but at least we don't get ripped apart, and we can sort of stay here forever, to the extent that, I don't know how long civilization lasts, but anyway.
Okay, further questions? So I think one, then two.
I came in late, so I might have missed this.
Yeah, it is actually mentioned in a report. And as you may know, the World Wide Web, of course, is something very important for the commerce worldwide these days. Probably trillions of dollars are spent on it. But it was actually born at CERN for the purpose of sharing scientific data among the researchers who are at different locations around the globe. So that's how World Wide Web started. And so that is already mentioned here as one of the spin-offs that already happened. And we expect, of course, many spin-offs to come once we develop new technologies like muon shot, which may be useful for all kinds of different purposes. So it is mentioned in there. Thank you.
Madeline?
Can you say that again? Well, so the gravitational wave detection is mentioned in a sense that this evidence for inflation is really about the gravitational wave coming from the expanding universe itself. And if that's the case, it is actually the first foray for us into the quantum gravity theory, because it is actually meant to be the uncertainty principle producing this graviton that eventually becomes gravitational wave, and that jiggles the CMB photons, and you can observe it at the end of the day. But you're right, we did not talk about gravitational wave detectors like LIGO within the particle physics portfolio, because we were still not quite sure if looking at the black hole mergers is something that would tell us, help us understand these basic questions about where the universe came from, what is everything made of. So they didn't quite fit into our definition of particle physics. So what we recommended in the end is that, well, theorists should look into this more to see how gravitational wave and particle physics are connected to each other. And maybe the next panel would embrace gravitational wave within the portfolio of particle physics if there's a good reason for it. So that's what we said in the report. I hope that makes sense.
Okay. Well, let's thank our speaker again for a wonderful talk.
Okay, thank you.